All right, let's get started. One sec to turn over. Okay. Get this clipped over. Good. I didn't mention the Halloween festivities on the slides here. For some reason, my laser pointer doesn't like me this morning. But I will say that the lobby looks pretty cool. So if you get a chance to check out the engineering lobby and all the activities going on today, please do, because it looks pretty awesome. I was hoping to get the exam graded in time for class today. That didn't happen, but I definitely want to get it graded by Monday because advising is going to start, which is going to get pretty hectic I think for all of us. So one thing I will say, if you have not yet scheduled an appointment with your academic advisor, I would do so. Registration doesn't begin next week, but the week after. So if you haven't done so, please do so. Yes?
Are they still reassigning advisors for engineering students?
What?
Are they still reassigning advisors for engineering students? Like I heard they was reassigning advisors at the beginning of the semester.
What major are you?
Mechanical.
So they might have done that already. I would check, and the reason why was because, the reason why we sometimes do that every time is because as students graduate and go through the program, sometimes one advisor ends up getting a lot, and so they distribute accordingly. I would check DegreeWorks or MyMU because you probably already have it. Your department, I think, was one of the only ones that did this semester. Everybody else, I think, stayed the same. Any other questions? All right. So today, the example that we're going to do, I think, is probably pretty easy to understand if you understand everything we've done so far. Although, just got to be careful with bookkeeping on what we're going to do today with centroids and volumes. But this example is not going to take the entirety of lecture. And instead, what I'm going to do is spend the later part of the lecture talking about this, which is the concept of a moment of inertia. It's in a weird spot in the curriculum. Like you cover it in statics, you cover it in mechanics of deformable bodies. I kind of like to at least introduce it in here because it's very natural to discuss after a centroid, and it's very applicable in certain areas of engineering, but we'll get to that when we get to it. Okay, so let's talk about centroids of 3D bodies or volumes. And I think you could probably predict by now how we're going to do this. If you remember, if we wanted to locate a centroid, we're computing a weighted average of the areas. If we have a line group like a truss, but in your last homework assignment, we just compute the weighted average of those line segments. Well, for areas, we end up using our centroid references as well. For volumes, we're just computing a weighted average of the volumes. So if we want X bar, it's the sum of the X times the volumes divided by the sum of the volumes. For Y bar and Z bar, respectively, it's all the same thing. So instead of summing or integrating in terms of area, we're summing or integrating in terms of volume. Now, one of the interesting things about this is that by and large, a lot of times you're still able to utilize these as your centroid references. It is only when the shapes truly become, I would say, three-dimensional that you really need to worry about dealing with 3D centroid references. And so what I mean by that might be something like this. Like if you have an element that's, let's say, a hemisphere or a semi-ellipsoid. To be frank, we're not really going to worry about a lot of that in here. A lot of the components that we would need to be worried about in engineering are hopefully ones that we can break down into relatively easy cross sections to deal with. And so what we're going to do today is look at this part, this machine part, and we're going to look at determining the centroid of this machine part. Probably what we won't do is do X bar, Y bar, and Z bar. We'll probably just do one of them. But what we are going to do is break this down into simple shapes and compute the X, Y, and Z for each of the individual shapes. Because if you get that and you know how to compute, let's say, Z bar, well, then X bar and Y bar are incredibly incredibly easy to understand. So, and again, as I said, this is a 3D part, but I think we're going to be able to make use of a lot of our 2D references, and you'll see what I mean here in a bit. Okay. So let me make this a little bigger so that we all can kind of see what's going on. Now, in order to do this problem, we need to break this down into a series of simple shapes. And I kind of cheated a little bit because I've got the cross-section of this, or the schematic sort of copy and pasted over and over again, so I don't have to keep scrolling up and down. But the idea is that as we go about breaking this down, we can use this to sort of ensure that our bookkeeping is done appropriately. So what we're going to do is we're going to break this down into a series of what I would call simple shapes, okay? And so what we're going to have is we're essentially going to have 4 regions to deal with. We're going to have a rectangular prism right here. We're going to have this sort of quarter circle region right here, and then we're going to have 2 circular holes, okay? And so for each of these, we need to compute not only the x, y, and z for the centroid of these individual shapes, but we also need to compute the volume, okay? So let's start off with what I'll call shape 1, okay? And so shape 1 is a rectangular prism. And so let me try and draw this out, okay? Now, I'll show you the way I'm going to split this up, and probably the most important region to focus on is sort of this overlap region right here, okay? So let's look at this circular region right here. The radius is this corner part right here, because this is 2 inches down to this being 2 inches. So really what I want to do is break off that circular region. So I'm going to basically say that this is my prism. Okay? And what we'll do is we'll sort of do some dashed lines here and some sort of like dashed lines there to sort of indicate that that's the prism that we're looking at, okay? Now I'm going to redraw this prism sort of over here so that we're all sort of cognizant of the dimensions and the data that we need to consider. So it's going to look something like this. Okay, so there's our prism. And the first thing I want to do before I start identifying dimensions is I want to make sure that it is crystal clear that that point right here, that is the origin. So that when I start computing volumes and writing x, y, and z values for this shape, that I am using an appropriate reference. Okay, so let's see if we can put some dimensions on this prism. How wide is this prism along the x-axis? ½ inch. How about how tall is it along the y? Does anybody know what that is? 2 inches, exactly. While it's not explicitly called out for, that's where the radius of this circular region comes in. And how about the length along the z? 4.5 inches, exactly. So that means this dimension here So there we go. So in order to compute the volume, there we go. And 2.5 multiplied to give you 1 times 4.5 is 4.5. So that's going to be 4.5 inches cubed. But I also want an X, Y, and Z. Okay? And so what I mean by that is, would you agree that for a rectangular box, the centroid is, I don't know, somewhere about right there? So my question to you is that with respect to this origin, what are the coordinates of that point? Along the x-axis, what are the coordinates? 0.25. What about along the y? -1, not +1, -1. Because here's the origin, we have to go down to get to the centroid. And about along the z? 2.25. So this is going to be 0.25 inches. I honestly think that's like the hardest part, is just making sure you can compute the volume and identify the coordinates of the centroid for each individual region. You can do that. The rest is cakewalk. Okay? So everybody okay with this? Now let's go to shape 2. Okay? Now in this case, let me move this down a little bit. So in this case, shape 2, is this quarter circular region. Now I'm going to scroll up a little bit because we got to make sure we don't overlap. Okay, and here's what I mean by overlapping. Would this be the quarter circular region? If I define the quarter circular region like this, to go from here all the way over, would that be right? You're shaking your head no. Why? Because I already counted for this little wedge over here. Okay, that's exactly right. So what that means is that region's got to look like this. That's the region of interest. So you can see between the two, between this region and this region, you can see I'm not overlapping. I'm not double counting area. So now I have the unenviable task of trying to replicate this schematic over here. I will do my very best. So let's see. I think I did all right. I think I did okay. Okay. Now, is the origin right here? No, the origin's actually like somewhere over there. So let's make sure we account for that. So if I take this and do that a little bit, the origin actually goes right here. This is the Z, that is the X, that is the Y. So you have to identify those appropriately. Now let's put some dimensions on this. We know that That dimension is 0.5 inches. We know that the radius is 2 inches. And we know that this dimension right here is 0.5 inches. Okay? So far, so good? All right, so in terms of volume, so let's see if y'all know how do we compute the volume of this shape? So maybe what we should do is compute this area right here, multiply by the thickness, right? So we have a pizza slice, right? That's a quarter of a pizza. So we compute the area and then how thick the pizza slice is, right? So it's going to be something times the thickness. So here, let's expand that a little bit. And how do we compute the area of that pizza slice? Well, how do you compute the area of a circle? Pi r squared divided by 4, right? So maybe what I'll do is something like that. So pi r squared over 4. So I can go ahead and give you that. I'll chug that out for you. Ends up being 1.571 inches. Okay. So now we need an x2, a y2, and a z2. Now one of these is easy. That's z2. What's z2 going to be? What's that? Quarter of an inch? But the other one, not so much. You may not remember that one, but that's why we have centroid references. That's why we can go back to, to this. And it's funny how I'm looking at the centroid references for a 2D region, not a 3D region, because really all this is a two-dimensional region that's been extruded. Okay? So if I have a quarter circular region, x bar and y bar is 4r over 3 pi. It's the same thing we have over here. So what I can do is I can say x bar is 4r over 3 pi. But is that right? I have to add half an inch. That's exactly right. Because 4r over 3 pi will get me from here to the centroid. But from the origin, I have to shift over another half an inch. Oh, drop my pen. Okay. I'll help you out with that one. Now, what about y2? What's the formula going to be for y2? This is 4r over 3 pi plus a half an inch. What's y2 going to be? Do we have to add half an inch? We're just going down. But that's the key word. Say it again. Negative 4r over 3 pi. Exactly. I think you could probably guess what that would be based on the other one. So is that so bad? All right. Let's bring this back up. Now, for shapes 3 and 4, man. We kind of need to come up with a numbering scheme. So let's call that one 3, that one 4. Just doesn't really matter. We just need to pick one. Now they're both going to have the same volume. All right? And again, this is a circular region that's just been extruded. So the volume is going to be pi r squared times the thickness. But is that formula accurate? Shaking your head no, why? It's a hole. It needs to be negative. It's 100% right. We're removing that area. Now, the problem said that these were 1-inch diameter holes or 1/2 inch radius holes, and the thickness is that. And so when it's all said and done, you plug and chug, you get negative 0.393 inches to the third. I just realized this whole time I've been saying the volume is inches. That's wrong. That's inches to the third. Oh, okay, I got it right on the first one. Yeah, that's inches to the third. But in order to do this, we're going to need also an x3, y3, z3, and we're going to need an x4, y4, z4. So let's do the x's. How far is it from the origin to the center of these holes along the x-axis? Say it again. Exactly, and that's the case for both of them. All right, what about y? How far is it from here to the center of these holes? -1. That's exactly right. Really, the only one that changes is the z. So, how far is it from here to the center of this hole? We'll start with just 3. 1.5 inches. It would be very easy to say it's 1 inch, but remember, 1 inch goes from here to here. You have to go another 1/2 inch to account for the thickness of the material. So this is 1.5. What about Z4? 3.5 inches. What's that? Oh, 25. Does that make sense? Okay, so what I'm going to do is, I'm going to compute now the location of the centroid. But I'm only going to do one of them. I'm not going to do all 3, and you'll see what I mean. Once you do one, the rest are pretty easy. So what we'll do is we'll say we have a shape. Let's write our volumes. So our volumes were 4.5, 1.571. Those were our two holes. So I can sum those up. When I sum them up, I get that. And like I said, for this calculation, I'm only going to do the z-axis. But if I did the x and y, it'd be the exact same. So now what I'm going to do is list the z coordinates. That was 2 1/4. That was 1/4. And then you can see the z3 and z4 right up there. And so now we're just going to multiply the two. I know the units might be a little weird, like inches to the fourth. Like, are we entering the fourth dimension? That's just a moment of area, or a moment of volume. So what do? We just do that times that, that times that, that times that, that times that. We just chug it out. Given that this is simplistic, I'm just going to do this one for you. So this is 10.125. This one's 0.393. This one ends up being negative 589, 0.589, negative 1.374. And when you sum that up, you get 8.554. So therefore, Z bar is just the sum of, sorry, I'm still not sure about that. I am, it's okay. I guess I put my leg up and I woke up Siri. All right, my phone's haunted, but it's Halloween, that makes sense. Come on, I'm gonna have jokes. All right, so 8.554 inches to the fourth over 5.285 inches to the third, and you all can chug that out. Ends up being 1.618 inches. So you see, I mean, I'm happy to do X and Y, but I really don't think it'd be any more difficult. You just do it again and do it again. So, because I really want to have some time to discuss this whole moment of inertia thing. Any questions? All right. I kind of want to talk about this concept of the moment of inertia, and because I really want to make sure that this has its moment to shine, if you will, in the land of engineering 213. So let's talk about this. Now, I've been using this term moments of area, but I want to sort of formally define this a little bit better for you. So if I wanted to determine the area of a region, essentially what I'm doing is I'm defining these little dA elements, these little dA rectangles, and I'm summing them up, right? Well, if I multiply x times dA and sum those up, I'm computing a moment of area. I'm computing the first moment of area. And we've seen this before, because if I take this integral and divide it by that, I get the centroid, okay? So that is a first moment of area. I could define a second moment of area. I could define a 56th moment of area. And basically it would just be that differential element of area multiplied by that distance, however many times, or by that moment arm, however many times I deem appropriate. So like the 57th moment of area would be the integral of x to the 57th times dA. Now, are we going to do that? No. But as engineers, we are going to do the ones that have specific usefulness. Okay? This one was useful. Okay? And it was useful because it was needed to determine the location of the centroid. This one is also useful, okay? This has a very specific name. That second integral, that second moment of area, we have a very specific name for that. We call it the moment of inertia, okay? It has a very important and profound impact on structural response, okay? And to explain what that means, I want to show you this, okay? So this is somebody framing out a floor system for a deck or an elevated platform in their backyard. Maybe it's for a shed, a floor for a shed or a deck or what have you. But I'd like to look at the floor beams. Notice how they're oriented upright, like they're sticking upright. Why? I mean, ignore everything I just said earlier about math and integrals and equations. Why stick the floor beams up like that? Why don't you stick them flat? Say again? It's harder to flex the beams that way. In other words, the beams are stronger that way. But why? I mean, common sense tells you that, right? But why? I'm asking you why, okay? I posit to you that the reason they are stronger that way is because along that orientation they have a larger moment of inertia. Okay? That's what the moment of inertia is, essentially. Okay? In a nutshell, at least for the land of structural mechanics, and when I say structural mechanics, I don't mean just civil engineering. I'm talking about anything where you're taking an element and applying force to it. Okay? So this is going to apply to you mechanicals designing machine parts and you biomedicals designing implant devices or anything that you're going to do. The orientation at which you apply forces has a profound impact on how it's going to perform, okay? And even for you biomedical engineers, right? Not to get too much of a gruesome example, but if you have, let's say, you want to assess the amount of force is required to break, let's say, a given bone. Well, it's going to depend which way that force is facing. In other words, if I have my leg, how much force does it take to break my leg if it's going this way? Or what about this way or this way? The orientation at which you apply that load is going to cause different answers for that question. You see what I mean? Okay. This is a simple example to kind of wrap your head around it, but there are applications in just about any field of engineering. Okay. And so that orientation here, I think it makes sense, but I'd like to apply some mathematical rigor to it. Okay. What we're going to do is we're going to go about looking at the moment of inertia of like a basic region like this. And remember, we kind of did this before. Remember, we did this problem before. We looked at this region, and I want to show you what happens about when it comes to computing the moment of inertia. Now, just to make sure that we're connecting this to concepts that we've already done, remember, we had one homework assignment where I made you derive a formula. But then past that, we said, look, we're just going to use the formulas to compute the moment of inertia of composite, or compute the centroid of composite shapes. Same thing's true with the moment of inertia. Okay, so it's going to be a pretty straightforward algorithm, but we'll get to that later. So let me refresh everybody's memory real quick. We had done this shape before, and we found the location of the centroid of this region. Okay. And the way that we did that is we first started off by integrating, dA, right, to determine the area, right? And so we defined what this rectangle looked like, and we said, okay, let's integrate. We got an area of 9. And then we computed our first moments of area. So we calculated the integral of x dA, got x bar, then computed the integral of y dA. Got y bar. So now all we're doing is computing the integral of y squared. Shouldn't really be anything that's all that challenging, but just trying to connect this to some stuff that we've already done before. So what I'll do is I will say Remember the subscripts were flipped? Remember that? Remember how the integral of x dA, we called that qy, right? And remember we did that because how far is it from, let's say, the y-axis to our centroid? From the y-axis to our centroid, that coordinate is x, right? And so this was the integral of x to the third dx, which memory serves. Hold on, let me turn back to what we had done before. I don't want to keep going back and forth here. So the integral of x dA, that was 81/4. Then we had this. And with this one, what we had is the integral from 0 to 9 of y, and then it was 3 minus the square root of y dy, which ended up being this. Because remember, we had note we had that dA was either equal to x squared dx or dA was equal to 3 minus the square root of y dy. And so all we're going to do for the second moment of inertia, again, I think you're going to find this is pretty simple, is if I want to find, let's say, the moment of inertia with respect to the x-axis, okay, all I'm going to do is I'm going to integrate y squared. Okay, that's all I'm going to do. And so just like before, I'm going to integrate from 0 to 9 y squared of this, which is going to be the integral of 3y squared minus, if I have y squared times y to the 1/2, so that's y 5/2, not 5/5. And that's should be a pretty easy integral to evaluate. Am I correct? I mean, I'm hoping. So that would end up being when you chug it out. And then the same thing with this. So IY is this. This one's easier. And so when you chug that out, you get that. Oh, that's not approximate. That's actually. Yeah, no, it's approximate. Now, would it make you feel better if I told you you aren't going to have to do any integrals on this? Would that make you feel better? You're not. Don't worry. But I want to make a point with this. When you chug this out, you get, these are the numbers that you get, okay? And I'm not really interested in going through and turning this into another Calculus 1 lecture. But barring me going through and chugging out the integral, would you all just take these at face value to say that these are the answers to these integrals? Are you believing me on this? Okay. All right, let me show you something. Let's go back to let's go back to this image, okay? I posit to you that the moment of inertia is a function of what orientation that you're looking at. And then if I were to compute the moment of inertia of, let's say, a rectangle, I would get a larger value, let's say, for Ix than I do Iy, okay? Now, I think that just based on our last example, it should make sense that you're computing different integrals, right? So you should get different answers. And one's probably going to be bigger than the other, okay? I posit that for a rectangle, you're going to get a bigger moment of inertia about the x-axis than you do about the y-axis. And that moment of inertia is a reflection of flexural stiffness. It is the reason why if you are building a porch in your backyard and you're using wood as your floor joist, you face them up like this, not like that, okay? Because the moment of inertia will be larger in that direction than it will the other. To point that and reference that to the example that we just did, all right, let's just look at this shaded region. Do you notice how the shaded region is kind of like more vertical than it is horizontal? It is almost if this vertical or this shaded region is oriented kind of in the same way that our wooden floor joists are in our wood deck. And notice how we're getting a larger moment of inertia this way than we are this way, okay? Stands to reason that if instead of a rectangular beam, my beam looked like this, that it's going to be stronger this way than it is this way, okay? And that's what the math is telling us, okay? Now, are we making floor beams that look like this? No, we're not. But we are making floor beams that look like this. That's very common, right? That is incredibly common. So how do I determine the flexural stiffness of something like this? Well, how do I do it? I break it down into simple shapes, right? Because that's just a bunch of rectangles. So we're going to apply the same idea on Monday. The idea is we're going to take a realistic example, break it down into a series of simple shapes, and we're going to apply an algorithm to compute the moment of inertia. So the way that that algorithm works is it starts by locating the centroid, and then we apply this algorithm later. The name of that algorithm is called the parallel axis theorem. I will explain that on Monday. I don't want to information overload you today. Plus, I feel like giving you 5 minutes of your life back. I'm going to pull up the QR code again. That's all I've got. I will see you all on Monday.